All right, so let's look at this one. We've got the function, again, is trigonometric, so the domain has been restricted for us so that we don't have an infinite number of them, because otherwise our critical points would start getting to be a little out of hand. All right, so our domain is restricted. That's already done. Now let's just take the derivative. We get derivative is 1/2 plus cosine of x, and I want to know where is this either 0 or undefined. Certainly this is never undefined, so I'm really just solving where is cosine of x equal to -1/2. So that's going to happen on this interval at 2/3 pi and again at 4/3 pi. So I set up my number line, and again, I really don't want to go to the left of 0 or to the right of 2 pi, so it's not really my full number line. And then I'm breaking up values at 2/3 pi and 4/3 pi. So I'm choosing a value between 0 and 2 pi over 3 and checking what the derivative is. I will get a positive result, then negative, then positive. So my function is increasing, then decreasing, excuse me, then increasing again. So if I'm going from increasing to decreasing, I have a local max at 2 pi over 3 comma something. And then I'm going from decreasing to increasing, so I'm going to get a local minimum at 4 pi over 3 comma something. To get the something, we always plug back to the original function. So in fact, I didn't give myself quite enough room here. Let's change my... Okay, so I plug 2 pi over 3 in. I get pi over 3 plus the square root of 3 over 2. And if I plug 4 pi over 3, then I get 2 pi over 3 minus the square root of 3 over 2. Both of these, if you want to know like decimal approximations, this is like 1.228, and this value is like 1.913 for the sake of graphing. Okay, let's do the same thing again for the concavity test. So second derivative is going to be negative sine of x, and I want to know where is this either 0 or undefined, but of course sine of x is only ever going to be, it's always going to be defined. So we're really looking at where is negative sine of x equal to 0. That would happen on our at 0 and at pi and at 2 pi. Now of course we're only looking at values between 0 and 2 pi, so this still is really only breaking this up into two intervals. So we're looking to the left of pi for the second derivative. Oops, I just realized that says f. That should say f prime. This should say f double prime. So between 0 and pi, we get a negative result for the second derivative, and then we get a positive result for the second derivative. So we are concave down and then concave up, which gives us an inflection point at pi, comma, if I put pi in there, I get half a pi plus another, no, plus 0, right? So that's just half of a pi. All right, so we put all these pieces together, right? So when I go to graph this thing, I'm only graphing between 0 and 2 pi, so I don't need to go. So there's 0, and I'm going to be stopping at 2 pi. So at pi, I know I have an inflection point. That's going to be at half of a pi. And then I've got a local max at 2 pi over 3. And I would have to just sort of estimate where 1.913 would be. And then at 4 pi over 3, I've got a local minimum. Again, estimating that 1.2. Okay, so from 0 to 2 pi over 3, I'm increasing that whole time in a concave down fashion. So increasing concave down, hitting my local max, and then I am decreasing, still concave down. And then I hit my inflection point, so now I switch to concave up, decreasing. Oh, pretend I hit my point there. And then I'm going to stay increasing, but I'm going to switch to increasing, and stay concave up. And now I'm not going to put an arrow at the end because I really am just starting at 0 and ending at 2 pi. If you wanted to know those actual values as actual points, you could plug them back to the original. So I did recognize that at 0, when you plug 0 back into the original function, that is an intercept. So I do get 0, 0. And then here I would get some other value. But again, this is enough for the sake of our sketch. So there's no need to do like end behavior here or anything like that because we're not looking at the ends of it. We're just looking at a very finite piece of the domain. So there you go.